In this video, we look at what's called Doppler shift. Now, as we have seen that when light is traveling with respect to an observer, whether the observer is at rest or moving at a certain speed, it doesn't matter. As far as the speed of light is concerned, it's always measured to be 3 times 10 raised to 8 meters per second, regardless of the relative motion between the source and the observer. There are, however, certain properties of light that do change depending on the relative motion of the observer and the source. In this video, we will talk about two properties, namely frequency and wavelength, that are affected by the relative motion of the observer and the source of light. So wavelength and frequency, this should be a Y. So to understand why frequency and wavelength are affected by the relative motion, let's consider a source of any kind of wave. It doesn't have to be light, but any kind of wave. So here is a source. Source S, and then this is emitting a ray traveling in all directions, and then here is an observer which is recording, or which is looking at these waves. Now, if the observer and the source are stationary with respect to each other, then the waves come at the observer at a certain rate, and that determines the frequency of the wave and its wavelength. Now consider the situation that the observer starts to move away from the source. So if the observer is moving to the right and the source is stationary, then the rate at which the wave fronts will reach the observer become slower. So there'll be more gap between the successive wave fronts, which basically means that the wavelength would be would be larger, or the frequency would be smaller. So fewer wave fronts will reach the observer per unit time. So that's a smaller frequency. On the other hand, if the observer was moving towards the source, so if this is the source here, and then that's the observer, and these are the wave fronts coming from the source. And if the observer moves to the left towards the source, then more and more wave fronts will pass the observer, will reach the observer per unit time than before, which means now the frequency of the wave appears to be larger. So that's basically the idea. This change in perceived frequency and wavelength is called Doppler shift. So the two situations to think about: if the observed wavelength is longer than that emitted by the source when the two are moving away from each other. So in the first case, when the observer was moving away from the source, the wavelength appeared to be larger, or the frequency appeared to be smaller. And that's known as red shift. That's a red shift. Red, because red, you will recall, in the visible spectrum is the largest wavelength end of the visible spectrum. So that means the wave seems to be shifting towards the red part of the spectrum. In other words, its wavelength is increasing. Now, what I drew here was the situation that the observer was moving away from the source, but the same is true if the observer was stationary and the source was moving to the left, you would have exactly the same situation. So what's important here is the relative motion between the source and the observer. It doesn't matter which one is moving, they could both be moving. As long as the relative motion is away from each other, there'll be a red shift, or the wavelength would be observed to be longer. In the other situation, if the two are moving towards each other, then the wavelength appears to be shorter, or the frequency appears to be larger. Shorter wavelength end of the visible spectrum is the blue end. So for that reason, this change in frequency and wavelength is known as blue shift. It's as if the wave was moving towards the blue end of the spectrum. So these are two types of Doppler shift that you have. Now, the idea of Doppler shift existed in classical physics also, but the equations for that are somewhat different in special relativity. And these are the equations that we use to figure out the observed frequency and wavelength. In these equations, lambda s is the source wavelength, meaning the wavelength you will observe if you were at rest with respect to the source. Lambda observed is the observed wavelength when there is relative motion, and u is the relative velocity of source to observer. Now, in using this equation, in these equations, you have to be careful because u can be positive or negative. So keep in mind that u will be taken to be a positive number if the observer and the source are moving away from each other, and it would be taken to be a negative number if they're moving toward each other. This is how you calculate the observed wavelength. The first equation represents the observed wavelength, and lambda s is the wavelength that would be observed if there was no relative motion between the two, and then u is the relative velocity, and c is the speed of light. Similarly, there's an equation for observed frequency, how that is different from the frequency that would be seen if there was no relative motion, and that's Fs. There are many practical applications of Doppler shift, since if you measure the wavelength of some kind of wave coming from stars or galaxies, and that can, if you can measure the wavelength, and if you have other means to figure out what the wavelength should have been, then you can use lambda observed and lambda s to figure out what u is, or what the speed is. So this can be used to measure position and velocity of stars and galaxies. Even at a smaller everyday scale, Doppler shift is used for weather forecasting, to figure out the speed at which certain weather systems are moving. Basically, you have a wave, a sonar wave, which moves towards the clouds, and then it's reflected back from there. And then if you compare the incident wavelength and the reflected wavelength, that allows you to calculate the velocity of the weather system. So in weather forecasting, if you might have heard of the term Doppler radar or Doppler satellite, and that's basically what they're talking about. It's the use of Doppler effect to make predictions about the weather. Similarly, the radar gun that the cops used to measure the speed of moving vehicles also involves Doppler effect. So you send a radar wave of a certain wavelength and it bounces back from the cars, and then we can compare the incident wavelength and the reflected wavelength, and then you can use those to figure out the speed of the car. Okay, let's look at problem number 24. Let me pull up the book here. So problem 24. If a galaxy moving away from the Earth has a speed of 1,000 kilometers per second and emits 656 nanometer light, characteristic of hydrogen, the most common element in the universe, A, what wavelength would be observed on Earth, and B, what type of electromagnetic radiation is this, and C, why is the speed of the Earth in its orbit negligible here? So let's record the given information. You have the relative speed of the two, which is 1,000 kilometers per second or 10 raised to 6 meters per second. And when you say that the emitted light is a 656 nanometer, presumably that's what you would measure if you were at rest with respect to the source. So lambda s is 656 times 10 to the negative 9. Nano is negative 9. And then we have to figure out what wavelength would be observed on Earth. So lambda observed is what we are looking for. An important thing to keep in mind is that the galaxy and the Earth are moving away from each other, and therefore U is taken to be positive 10 raised to 6. If they were moving towards each other, it would be negative. So then you just plug in the numbers. C is, of course, 3 times 10 raised to 8, and it gives you an answer of 658 nanometers. So the original wavelength was 656 nanometers, and it's perceived to be 658 nanometers. So it's so it's a small difference, and yet it is a non-zero change. And then you can look up the wavelengths of the visible spectrum, and you will find that 658 nanometer corresponds to the red light. So what type of electromagnetic radiation is this? It's red light. And then the third part of the problem asks, why is the speed of the Earth in its orbit negligible here? Basically because the orbital speed of Earth is much, much smaller than the speed of light. So it really doesn't affect anything. So that brings us to the end of 28.4, and we will look at relativistic dynamics in the next few videos, starting with relativistic momentum.